what I'm going to do now is I'm going to introduce an important concept relating to the energy flow, and it's called the Poynting vector. The Poynting vector. The Poynting vector, we call it S. Okay, it is defined to be 1 over mu naught E cross B. So whenever there's electric field E and a magnetic field B, as long as they're not parallel to each other, you can define a non-zero Poynting vector which equals this. If you take a look at the Poynting vector and compare with the result for the electromagnetic energy flow that we got in the previous page, okay, you see the difference here? There's no 1/2. See, there's no 1/2. But again, that 1/2 is only because you have a time average value. So E maximum, E is not always equal to E maximum. B is not always equal to B maximum, right? Because the wave has to go up and down over one cycle, and that's what 1/2 comes from. But in the most general case, okay, when you have the electric field E and the magnetic field B, this Poynting vector gives us the rate of energy flow per unit time, per unit cross-sectional area. Okay, you don't have to do the time averaging, so the 1/2 is not there. So that's some sort of instantaneous value. This energy flow, Poynting vector, is not only valid for the case of electromagnetic waves. In fact, it is valid for any cross E and B field. There is always an energy flow associated with electromagnetic field. If both fields are present, E cross B, we can use the Poynting vector to figure out the rate of energy flow. So once again, what is the meaning of the Poynting vector? It is equal. First of all, its magnitude equals to the intensity carried by the electromagnetic field. In other words, the energy flown past a certain unit cross-section area per unit time. And its direction is the direction of the energy flow. Okay, again, this is valid whether or not you have an electromagnetic wave. As a matter of fact, to illustrate that, what I'm going to do is we're going to take a closer look. Okay, we're going to take a closer look at an old problem that we saw some chapters ago. Suppose you have a long straight wire which carries a current I. Okay, which carries a current I. The current flows this way. Okay, from down to up, and it's got a it's got a radius R. Actually, let me call it radius A because I don't want to confuse with the resistance. Radius is A. Okay. In order to support a current this way, there has to be local electric field pushing up like this. And since you have an electric field, there is also a magnetic field going around it like this, right? So it's right on the surface. I can draw E this way and B that way. Okay. So if I use the Poynting vector, I found there's a Poynting vector E cross B which is inward. Okay, which points directly into the center of the wire. Okay, what is the significance of this Poynting vector applied to this problem? See, this is not an electromagnetic wave problem. Okay, you can have a constant E, constant B, right? Now we know that as the current flows through it, it's going to pass through the resistance, and therefore it's going to generate heat. Okay, how much heat is generated? It's at the rate of power consumption. That is the rate at which electromagnetic energy turns into heat, is I squared times R, right? Okay, thermal power, I squared times R. R is the resistance. Okay, now suppose I have a segment of this wire of length L. Okay, of length L. I want to know what is the total power converted into heat from electromagnetic wave. I know what that is. That would be P equals to I squared times R. R is the resistance. Okay, R is the resistance. And I can find R from the cross-sectional area, the length, and the conductivity or resistivity. Okay, in fact, this is rho times L over A, and L is the length, A is the cross-sectional area, which is pi A squared, and L is and rho is the resistivity, which is the inverse of the conductivity. So I can write this as I squared 1 over sigma. Sigma is the conductivity. L pi A squared. Right? That's the thermal power. Okay, thermal power. Meanwhile, when heat is generated with this at this rate, it is converted from electromagnetic energy, right? Now my question is, how is electromagnetic energy transmitted? A lot of people thought that the energy, the electromagnetic energy, is carried by the current going up like this, okay? Going up like this. Well, is it really true? Well, you know, electromagnetic energy is turned into heat, and heat is dissipated radially outwards, right? You know, that's radially outwards. So if you want to balance this energy output, you probably would guess that the electromagnetic energy has to flow radially into the wire, just as heat flows out of it, right? Okay, is that true? Well, you see, this pointing vector actually E cross B is actually pointing into the center, so that seemed to make sense. But by definition, S, okay, is the amount of energy going through a unit cross-section area per unit time. Now, if I integrate S over the entire side area, then what I should get is the total amount of energy passing through the entire cross-sectional area, the entire surface of the wire per unit time, right? That is the rate at which energy flows in electromagnetic form. It should cancel with the rate at which thermal energy flows out of the wire radially outwards. In other words, I suspect from conservation of energy that you integrate S dot dA over the entire side area, you should get that P. See? That's what you suspect. It would be wonderful if that happens. Okay? Again, this area A is the side area. It's the side area. Okay? So the entire side area. You don't have to worry about the top and bottom because the pointing vector is inward. It doesn't have any dot integral going up or going down. But before we can do this calculation, please make sure you attach a negative sign. You can see that because S goes inward and dA by definition is a vector going outward, so that's why S dot dA itself is negative. You have to cancel that with another negative sign. Okay, this negative sign simply means the current, the electromagnetic energy flows into the surface, not out of it. Okay, so S dot dA. Let's finish this integral. Let's see if this is true or not. Okay, let's test this question mark. First of all, S dot dA is S times dA times -1 because S goes in, dA goes out, so S dot dA cosine theta is -1, which cancels with this negative sign, so that's perfect. Secondly, because of the symmetry of the problem, S is the same in magnitude throughout the entire surface of the wire, so I'm going to take that S out. What's left is just the dA. What is that? That is the surface area of the side of the wire, right? And that is S times what? 2 pi A, that is the circumference, times the length L. Right? Okay, let's go further. What is S anyway? Look at this formula. 1 over mu naught. E cross B. E and B are perpendicular to each other, so it's just E times B. Okay, E times B. On the surface of the wire. And then times 2 pi AL. 2 pi AL. Okay, what is E and what is B? Well, let's see. E is the electric field, and to power an electric field, I need to power a current through it. I need a certain electric field. How are they related? Well, remember J equals sigma E. Okay, J equals sigma. J is the current density, so J is equal to I over pi a squared, and that equals sigma times E. And with that, I'm able to rewrite the electric field in terms of the current, which is what I want. See, I want a current here, okay? So, what is E equal to? I over pi a squared over sigma. So, I over pi a squared over sigma. That's E, okay? Then times B. What is B? Well, what does Ampere's law tell you? B is equal to mu naught I over 2 pi R. R is the radius because you're looking at a point right on the surface, a distance A away from the central axis. So this is 2 pi A. Okay, so that's B. This is E, this is B. And then don't forget there is another 2 pi AL. Okay, so another 2 pi AL. Okay, let's clean things up a little bit. Mu naught and mu naught cancels. 2 pi A and 2 pi A cancels. What do we have left? There's an I squared. Okay, there's an I squared. What else? There's a pi a squared. There is a sigma. What else? There's an L. Okay, there's an L. Okay, look. Take a look at this in there. See, this is the power, and this is the right hand side, the left hand side. So indeed, this is correct. Okay, and that's quite amazing, because you can see here the energy is exactly balanced. Okay, electromagnetic energy actually flows radially into the interior of the wire from the surface. Okay, not along the direction of the current, rather flows radially inward, and thermal power flows outward, and the rate at which electrical energy flows in exactly equals the rate at which thermal energy flows out. And that way you have the conservation of energy. Okay, so this is a very convincing example of the application of the Poynting vector. Okay, the electromagnetic wave certainly carries a flow of energy. Okay, so you have imagine there's a flow of energy carried by the electromagnetic wave, and when they meet something, when they're stopped by something, let's say I use a mirror, whatever, I use a wall to absorb it or to reflect it, and then they're going to exert a force, right? You imagine there's a flow of energy, and they got stopped by something, though they're going to react with it, interact with it. So basically, they will impinge a force upon the wall, upon the mirror, whatever. So the next question I have is, how much momentum is carried by the electromagnetic wave? Okay, and it turns out that there is a relationship between the energy carried and the momentum carried. The way you derive this relationship is not something we can study here. Okay, it's not something we can study here. You need more advanced math to do that, but I can tell you what the result is. Okay, I can tell you what the result is. The energy and momentum of the electromagnetic wave are related by this: momentum P and energy U. They're related by P equals U over C. A very simple relationship. So this is momentum, this is energy. So they're proportional to each other, and you can check the units. Okay, you take energy divided by the speed, you will get the unit of momentum. And but what we need to know is usually we don't care about momentum, but rather when an electromagnetic wave or beam of light, for example, shines upon a surface, it carries momentum, right? It carries momentum, and when that momentum gets stopped or reflected by the mirror or by the wall, how much pressure does it exert on the wall? Okay, this is something we care more about. This is, by the way, called optical pressure. Okay, optical pressure. And of course, pressure is the force delivered by the electromagnetic field divided by area, right? Divided by area. So how is this optical pressure calculated? Well, the force is equal to the rate of change of momentum. Okay, the rate of change of momentum. Now, the incoming electromagnetic wave has an intensity S. Okay, has an intensity S. That is the energy carried per unit time, per unit area. All right, energy carried per unit time, per unit area. But energy and momentum related like that. See, the energy and momentum of the electromagnetic are related like that. So the question is, how much momentum is carried by the incoming wave per unit time, per unit area? That would be S over C, right? That would be S over C. Okay, again, this is the momentum carried by the incoming wave per unit time, per unit area. If all this momentum turns to zero after hitting the wall, which means the wall is a perfect absorber, okay, this is the initial momentum, the final momentum is zero, right? So, per unit time, how much is the change in momentum per unit area? Okay, careful. The rate at which momentum changes over time is, by definition, force. And this is the rate at which momentum changes per unit time, per unit area. Okay, so what is that? That is force per unit area, which is pressure. So this is optical pressure. the pressure delivered by a beam of electromagnetic wave, which is a Poynting vector S. Okay, which is a Poynting vector S. All you have to do is divide by C. Now, I'm assuming that all this momentum get killed after they impinge upon a surface. So this surface basically is a perfect absorber. Okay, it does not reflect any wave. So this is total absorption. Okay, in other words, we say it's totally black, which does not reflect any light. On the other hand, another extreme case is when all the waves get 100% reflected. Okay, so the incoming momentum is u over c, outgoing momentum is negative u over c. All right, and that means the momentum change is now doubled. So the force or the pressure is also doubled. It's 2s over c. That is the case of total reflection. So we call it 100% white. Here, white means it's reflective. Here is 100% black, which means totally absorptive. Okay, in reality, we have, of course, something in between, right? A real, a real surface is neither totally absorptive or totally reflective. Okay, so it's always somewhere between S over C and 2S over C. S, of course, is the intensity of the wave, once I know that, divided by C, I can get the optical pressure. Now, usually when you stand in the sun, for example, you don't really feel there's a force upon you, right? So therefore, P should be very small in most cases. Well, let's take a look at sunlight as an example. For sunlight, okay, what is the Poynting vector value, time averaged for sunlight? In other words, what intensity is delivered by the sun on the surface of the Earth? Okay, this is a very important quantity. We give a big name. We call it the solar constant. Okay, we call it the solar constant. What is the solar constant? It is the intensity of the sun, of the sunlight reaching the surface of the Earth, actually reaching the upper atmosphere of the Earth. Okay, and it is equal to, we give the symbol like this, I, and this subscript denotes it's the sun. Okay, it's about 1.4 kilowatts per meter squared in the upper atmosphere. This is a big number for us to remember. Okay, let me explain to you what it means. It means that if you take a box, an intercept, okay, 1 meter by 1 meter, which is not very big, facing the sun directly, okay, in the upper atmosphere, you find that this area, 1 meter by 1 meter, will intercept about 1.4 kilowatts of power. In other words, it will intercept about 1,400 joules per second over just a 1 meter by 1 meter window. This is the so-called solar constant. Okay, it's a big number. You know, it's nearly 2 horsepower. So, in theory, if you can convert all this energy intercepted by only just 1 meter by 1 meter area from the sun, you turn it 100% into electrical energy, then the power output would be about 2 horsepower. Okay, isn't that great? So there is plenty of energy in the sunlight. Now, my question is, given this, that actually is the Poynting vector, time average Poynting vector. Okay, what is the pressure delivered by sunlight on Earth? Well, it will be this value divided by the speed of light. So solar pressure, so-called solar pressure on the surface of the Earth is about 1.4 times 10 to the 3. Okay, I'm using SI system throughout, and then divided by C, which is 3 times 10 to the 8. Okay, you can do a little calculation. You can then estimate the this pressure. Of course, the result is in Pascal. We can do a little calculation here. All right, 1.4 divided by 3, and it's about, to 1/6 figure is about 5, actually, or 2/6 figures 4.7 times 10 to the -6 Pascal. Indeed, this is very small. Okay, as a matter of fact, if you compare that with the atmospheric pressure on the surface of the Earth, that is about 100,000 Pascal. Here is 10 to the negative 6 Pascal. So no wonder you don't really feel the solar pressure. It's very, very small. But interestingly enough, okay, just for fun, you can do a calculation. You take the solar pressure, right? That is the pressure exerted by the sun on the surface of the Earth, and you multiply this by a very, very large area, such as the size of the state of California. What do you get? Well, you get roughly the total force of casted by sunlight, okay, on the state of California, right? Now, there is a saying that here in California we get tons of sunshine, right? Tons of sunshine. Now, my question is this literally true, literally correct, that we get tons of sunshine? Well, all you have to do really is to multiply this area, this pressure, by the area of our great state. Okay, you can do an estimation to find the size of the state of California. If you don't want to Google it, you can do an estimation. You know, California looks like this. Okay, more or less. Okay, and this distance from here to there, say a couple of 100 miles, and from here to there, maybe like I don't know, like 600-700 miles. From that, you can sort of estimate the area. Okay, you can estimate the area, and then you multiply this by that. You will see, you know, interestingly, a number, and that number tells you literally how much force does the light of the sun give to the state of California. Okay, so estimate the length, the width to be about 200 miles, and the length to be about, I don't know, 750 miles, you think? Okay, then the answer would be about 150,000 square miles. Well, actually, this is pretty close to the actual number. If you check it online, you will find the number 163,707 square miles. Okay, what we're getting is about 150,000, so we're not that far off. Anyhow, if you take the real number, okay, about 1.6 times 10 to the 5 square miles, and each square mile is about 2.56 times 10 to the 6 meters squared. You find the area A of the state of California to be about, you can do a calculation, about 216 figure, about 4 times 10 to the 11 square meters. Okay, you take that solar pressure, multiply by this area, what do you get? You get total force around 2 times 10 to the 6 newtons. And this is, you can convert that, okay? You can convert that to about 200 tons. Okay, so interestingly enough, the light of the sun impinged upon the state of California gives us a total force, which indeed is several hundred tons. Okay, so we literally do get tons of sunshine as an interesting notion.